Assalamualaikum and good day to Dr. Inam. My name is Nur Izzati binti Muhammad Zaini and my group members is Zaitu Khadijah binti Zahri. Today we will present our report Sound Wave Mechanic and their integration with electromagnetic system in engineering. In this presentation, we will explain the fundamental concept of sound wave and discuss how electromagnetic principles are applied in engineering system. For introduction, sound waves are mechanical disturbances that propagate through elastic media such as solid, liquid, and gases by means of particle oscillation. Unlike electromagnetic wave, sound wave require a material medium for transmission and cannot travel through a vacuum. In engineering application, sound waves rarely operate in isolation. They frequently interact with electromagnetic system for purposes such as signal generation, detection, processing, and transmission. This integration can be observed in devices such as a microphone, loudspeaker, ultrasonic sensor, and medical imaging system. Next, the objective of this report are to study the fundamental properties of sound wave and their interaction with electromagnetic system. We focus on the core parameter of sound wave, which are wavelength, frequency, and amplitude. We also discuss wave classification, including longitudinal and transverse wave, as well as standing wave formation and resonant phenomena. In addition, electromagnetic principles such as Faraday's law and the Lorentz force are explained in a relation to sound wave transduction and practical engineering application. Next, sound wave and electromagnetic system interaction. This slide illustrates the interaction between sound wave and electromagnetic system. Sound wave originate as mechanical vibration in a medium. These vibrations are converted into electrical signal using transducers such as microphone. The electrical signal are then processed using electromagnetic circuit, including amplifier and signal processing unit. Finally, the processed electrical signal are converted back into sound wave using device such as loudspeaker. This interaction form the basis of many acoustic and communication system. Next, fundamental parameter of sound wave. Sound wave are characterized by three fundamental parameters, which is wavelength, frequency, and amplitude. Wavelength is the distance between repeating point in a wave and is measured in meters. Frequency refers to the number of oscillations per second and determine the pitch of sound, while amplitude represents the maximum displacement of particle and is related to sound intensity and loudness. These parameters are related through the wave equation V equal to lambda F lambda, which is fundamental to wave mechanics. Next, we're going to longitudinal versus transverse wave. Wave can be classified based on the direction of particle motion relative to wave propagation. Sound wave are longitudinal wave where particle oscillation occur parallel to the direction of wave travel, resulting in compression and refraction. Other than that, in contrast, electromagnetic wave are transverse wave where the electric and magnetic field oscillate perpendicular to the direction of propagation, while transverse wave can be polarized, while longitudinal wave cannot be polarized. However, both wave types obey the principle of superposition. Next, we move on to standing wave and resonant. Standing wave occur when two waves of the same frequency and amplitude travel in opposite direction and interfere with each other. This commonly happens when an incident wave reflect from a boundary, such as a fixed or free end. With this interference, a stationary wave pattern is formed. Note a point where the amplitude is zero because of destructive interference, while antinote a point of maximum amplitude caused by constructive interference. Standing wave arise as a result of boundary condition and are important in many engineering applications. For example, in musical instrument and acoustic cavities, standing wave determine resonance and sound characteristic. In electromagnetic system, standing wave are formed in resonant structure such as waveguides and laser, where resonance is used to enhance a specific frequency.
Next, I'm going to continue with the reflection and boundary condition. Wave behavior is strongly influenced under three conditions. The first condition is fixed angle reflection with phase inversion. If it was an upward bump coming in, it comes back as a downward bump. This flip is called a phase inversion with a 180-degree shift. The second condition is free end reflection without inversion. The wave does not flip. If it was an upward bump coming in, it comes back as an upward bump. The third condition is match impedance, which is no reflection, and maximum energy transfer. The wave doesn't bounce back, so instead, all its energy keeps moving forward into the new medium. These mechanical principles are directly analogous to electromagnetic wave reflection and impedance matching in transmission lines, antenna, and waveguide. Next is electromagnetic principle in sound application. Sound's electrical energy conversion relies on electromagnetic law. There is three law, which is the first one, Faraday's law, used in dynamic microphone to convert sound into an electrical signal. If you move a wire coil in a magnetic field, you will make electricity. The second law is Lorentz-Force law, used in loudspeaker to convert electrical signal into sound. This is the opposite of the mic, which is if you send electricity through in a magnetic field, the wire will move. The third law is the piezoelectric effect, widely used in ultrasonic sensor and medical probes. These principles enable electroacoustic transduction in many engineering systems. For the case study used in medical ultrasound, there is two reasons. The first one is frequency range used. Ultrasound machines use very high frequency sound wave, far above what humans can hear. Human hearing range is about 20 Hz to 2000 Hz. The second reason is why sound waves are suitable because they are non-ionizing. Unlike X-ray, sound waves do not carry enough energy to damage DNA or cells. The third one is because of the role of the electromagnetic circuit, where the electricity power the whole process. The electromagnetic circuit is the brain and muscles that makes and interprets the ultrasound. Next is practical application. This include the first one, ultrasonic testing for flaw detection and material inspection. Probe sends high frequency sound wave into a material. If there's a hidden crack, bubble, or weak spot inside, the sound wave will bounce back from that flaw. The second one is used in medical ultrasound imaging and blood flow measurement, which the probe sends sound wave into your body. Different reflects the wave back at different speed. The machine uses these echoes to build a real-time moving image. The third one is used for acoustic communication, underwater communication system. The fourth one is the sonar and noise control, detection, navigation, and noise cancellation. As an example, a ship sends out a sound ping and listen for the echo to detect submarines, map the seafloor, or avoid underwater mountain. This system combines sound wave propagation with electromagnetic signal processing. For the conclusion, this report has presented the fundamental properties of sound wave and linked them with electromagnetic principles such as Faraday's law and the Lorentz force. The practical application demonstrate how electromagnetic system enable the generation, detection, and processing of sound wave. The integration of acoustic and electromagnetic technologies is essential for advancing modern engineering systems in communication, medical imaging, and sensing. So that's all from us. Thank you.